Okay, this is the second of the two problems in homework set 23 that I'm doing some videos on. Both of these have been application problems. The first was Newton's law of cooling. The second is a law associated with radioactive decay. And in fact, the problem says you have, I believe it's radioactive cobalt. It's got a half-life of 5.27 years. You start with 100 grams. How much will you have in 20 or 40 years? So a couple of things about this problem. It's a good time to talk about half-lives. I think we've talked about them in class probably beforehand. A half-life is a fixed time for exponential decay. It's a fixed time over which the function decreases by a factor of 2. So I'm going to draw this and then erase it later. So here's some exponential decay. Here's a time, I'm going to call it t0. Here's another time I'm going to call it t1. And the difference between those two I'm going to call t sub 1/2, the half-life. And this is the half-life if this value right here, t0, is twice this value right here, a0/2. So in one half-life, the value of the function drops by a factor of 2. And in fact, if we go out here to t2, another half-life, a0/2 will have dropped to a0/4. Every half-life is a step down of a factor of 2. There are other types of measures, and sometimes you'll see e-folding times. Same idea as the half-life. Here's tau 0, here's tau 1 in this case. Only the e-folding time, often written tau e 1/e, is such that if this is a 0 after one e-folding time, this drops by a factor of e, by a factor of 2.72. Same idea, factor of 2, factor of 1 of e. So that is Sugar probably yelling at a rabbit in the backyard. And she really needs to go outside to chase it, so come here, Sugar. There you go. Trust me, the rabbit is in no danger whatsoever. So let's go ahead and try to do this problem, but I wanted to do one more thing. So if the fundamental relationship for radioactive decay looks like this, and I'm going to write it like that. I like to have the minus sign. So in this case, k is going to be 0, so that e to the minus kt is going to decrease as time increases. Where the heck is the half-life in this? And you can find it very quickly, because if I put in t equals the half-life right here, and if the initial value was a 0, then the value of a t at the half-life is, as we've just shown, a0/2. And so now I'm going to be able to solve this equation. I'm going to get 1/2 is equal to e to the minus kt. I'm going to take the natural log of 1/2 is equal to minus k tau to the 1/2. Sorry, should have put in tau to the 1/2 right here. Tau to the 1/2. And now I'm going to solve for that, and it's going to be minus 1/k natural log of 1/2. And then generally the way you see this written is 1/k times the natural log of 2. You take the minus sign out in front, that is a factor, and raise it up as a -1 exponent on 1/2, turn 1/2 into 2 in that fashion. And in fact then 2, the natural log of 2 is 693/k. And there you have it. There's a relationship between the half-life and K. And we can go ahead and make use of that right away, because I can write down the formula that I want to use. Since I have this expressed this problem is expressed to us in terms of half-life, this fundamental equation, AT equals A0 e to the minus k, k then is equal to 0.693 t all over tau to the 1/2. So there's the form of this equation that we should use when it's expressed to us in half-lives. So if I just take this data, I'm going to write A sub t is equal to 100 grams, the initial value, and just because this is a little unwieldy, I'm going to write e raised to the exponent as exponent 0.693 t all over 5.27 years, and we're going to do all this work t in years. So we're ready to go ahead and answer the problem. Find out what A sub t is when t is equal to 20. So we've got A sub t is equal to 100 e to the 20 times 0.693 all over 5.27. I got to get out the calculator here and go 20 enter 0.693 times 5.27 divide. I'm going to store that right there. I'm going to need it later. E to the x. Why the heck is that a negative number or not a negative number? Because I didn't include this minus sign right here, which I really should have done. Let me go back, put a minus sign in, change sign, e to the x. Why did I get an error? Recall 0. Recall 0. Okay. Change sign, e to the x, and I have to multiply by 100, and I get an answer that says E at t is equal to 20, A at t equals 20 is equal to 7.2 grams. And I think I can do this very quickly if I put in 40. All I have to do is go recall this 2 times, change sign, e to the x, multiply by 100, and I get 0.52 grams in that case. If we could just kind of quickly do a sanity check on this. This half-life is a little bit more than 5 years. And so in 20 years, the cobalt has 4 chances to reduce itself by a factor of 2. So in the first half-life, it goes from 100 to 50, in the second one from 50 to 25, in the third from 25 to 12, and in the fourth down to 6. Yeah. And it goes to 7.2 because the half-life's not 5, it's 5.27. So that absolutely checks out. And so every what do I want to say? Every 20 years, it reduces by a factor of 7.2 divided by 100. So if I was to square that, think about that, then you would get 5.2, so 0.52. So I think we probably got the right answers there. And we can move on to homework 24.